It's my pleasure to introduce Professor Pierre Raphael from University de Nice, Sofia, Antipolis. He has got many awards, and I would like to. I would be happy to add an information that he will be awarded Grand Prix from French Academy of Science this coming October. And the title of his talk today is on singularity formation in Hamiltonian evolution equation.
So thank you very much, Professor Ozawa, for this introduction. Let me start by saying how a great privilege and honor it is for me to be given this opportunity to talk here at the ACM. What I want to do. Sorry, that's not working. Yeah, that's better. Yeah, so what I want to do is really to report on recent developments on the question of singularity formation for Hamiltonian evolution equations in the infinite dimensional settings. And the general context is the one of nonlinear dispersive equations. So very roughly speaking, the kind of phenomenon we are interested in here is nonlinear wave propagation, so propagation of wave in nonlinear media. And there are two main phenomena that occurs. The first one is dispersion. Linear waves want to spread. They want to spread their energy all over space. They want to propagate. And concentration, which is typically induced by some nonlinear effects. So depending on the physical context, it can become typically some gravitational attractive force, or it can be some focusing force when light goes through a crystal. Some kind of phenomena like this occur in fluid mechanics. And really, what we want to understand is the balance between these two phenomena of dispersion and concentration. So a canonical model that arises in many contexts that has been derived in particular in the 50s in various situations. It's a simplified model, which is valid in some approximation, and it's one of them, one of the famous one, is the nonlinear Schrödinger equation. So this is the following nonlinear partial differential equations. So you see here the linear Schrödinger group, IDTU plus Laplace U, and you see here this nonlinear term, u modulus of u to the p minus 1, and you have this plus sign, which is very important and reflects to the fact that I am modeling a focusing force. Something is forcing my linear wave, wants to spread according to the free Schrödinger group. This term here wants to force my wave to concentrate. Okay, and this equation has a very specific structure. It has it has the Hamiltonian structure, which is due to this very special non-linearity here, which I'm putting here, and this forces in particular some non-trivial conservation laws, and I'm going to come back to these kind of issues. Schrödinger equations appear typically in this form, or this is sort of the simplest model of this type you can write if you want. I'll tell you about another problem which has a similar Schrödinger structure, which is the so-called Schrödinger map problem. So the Schrödinger map problem has this following form. So it's DTU is U wedge Laplace U. It's a very simple equation. But the thing is that here U is a vector. Okay, U is a vector of R3. And typically what this equation means, it's a flow for function which goes, say, U is a function of T and X. X is in RD, but U is a vector, say a 3D vector, but it has norm 1. Okay, so it belongs to the sphere, and indeed this property is preserved by this problem. And this kind of problem typically arises in various instances. In the model of forward magnets of London Lifshitz, there are also strong connection to 3D Euler flows, vortex filament flows for the one-dimensional problem, and it has the wave and parabolic analogs of these problems are the so-called wave map problem and harmonic heat flow problems, which have been addressed by different groups of people, and in particular these wave map problems, which has attracted a considerable attention in the community for the past 10 years. Okay, so this is sort of another kind of nonlinear Schrödinger equation, and I'm going to discuss about it. Right? So the idea is just that, as you think, these are very simple models. The nonlinearity is very simple, but there is there is some structure hidden behind it, in particular conservation laws attached to this equation. So what do we want to know about this problem? We want to know everything. In particular, what we want to do is we want to have a qualitative description of the flow. Okay, really, what we want to do is to understand what solutions look like, what kind of behavior can we expect from this solution. So the first thing you want to do, and which was done starting in the late 70s, is to understand local solutions. That is, indeed, can you get yourself nice solution? There's an immense history about this problem, and roughly speaking, what you want to do is to have a good Cauchy-Lipschitz theory for this solution, that is, view your PDE as an ODE in a suitable balance space and have some sort of Cauchy-Lipschitz scheme to solve it locally in time, and this can be done, the key being the use of dispersive estimates. You need good estimates of the linear flow to indeed be able to show this kind of local existence. So for all the questions I'm going to look about, really, when I consider this equation, I want to put myself in the situation where the data is a very smooth, well-localized wave packet, right? I'm not going to talk about a regularity problem. I'm thinking of the nicest possible initial data, and I'm trying to understand what these solutions are going to look like. So in some sense, for the kind of question I'm asking, this is, if you want, simple. Then, if you want to understand globally what solutions look like, if you want to have a qualitative description of your flow, then one very interesting thing is to ask yourself the question of the existence of special solutions. And indeed, for the kind of problems we're looking at here, there are so-called solitary waves type solutions, and they take various forms. They can be either stationary, time periodic, or traveling waves. And the important thing here is that these very special solutions, they are propagated by the flow without deformation. They correspond, if you want, to bubbles of energy, or particle-like waves, which propagate without any deformation in the system. So there are typically, for these kind of problems, various ways of addressing the existence of these solutions. You have ODE methods, and you have also very clever methods from the calculus of variations, and particularly in the 80s, there's been lots of works on the existence of this kind of solitary solution. Then, so if you have your local solution, you have these special solutions, and now a very ambitious program would be to be able to completely describe all solutions, right? I give you a data. Can you tell me what the solution is going to look like? There is a famous problem in the field, which is the so-called soliton resolution problem, which is that in some settings, you believe that any data should decompose into a sum of these solitary waves, plus a remaining dispersion. So there are some progress on this. But the question I'm going to ask, I'm going to discuss today is the blow-up problem. Okay, what I want to understand, if you want, a solitary wave is a very special wave for which dispersion and concentration balance exactly. This is what produces this nonlinear wave that does not want to change its shape. What I want to ask today is the question of singularity formation. That is it possible that in fact, in some regimes, concentration wants to win? And indeed, the energy of my initial data, so I start with a very smooth, very nice wave packet, and what's happening is that the energy, dynamically, the evolution of the flow is such that the flow tends to concentrate my wave, and my wave will want to concentrate this energy maybe at some point in space, or maybe on a more complicated curve, I mean, in a way which I need to describe. So this kind of singularity formation problem, this kind of blow-up problem, so it typically forces my solution, if you want, it stops my Cauchy theory, if you want, in some space. So solutions typically live for a finite time. So what do we want to know on blow-up problem? Well, there are three kinds of questions. Of course, the first thing you want to know is, do blow-up solutions exist? And there are very famous cases where the existence of blow-up solutions is known, because what you can show is that there is no way they can exist forever. This is what I like to call an obstructive argument. And there are very old problems, and it's typically the case for the nonlinear Schrödinger equation. There is some magic algebra that gives you this information. But typically, even when this is known, it gives you very little information on the nature of the singularity formation. You know that your solution cannot be there forever, but what is going on, and can you describe the way it concentrates its energy? Typically, this is not given by this kind of argument. But if you can have one, it's already nice. What I really want to do today, and this is what I'm going to focus on, is give you a bunch of examples of precise description of the singularity formation phenomenon. Right? This is maybe, from my point of view, what was most missing, at least on this kind of problem. Just to start with its examples. Right? Can we actually build spatial solution and understand how this wave packet wants to form a singularity? And a more ambitious problem, of course, would be not only to show examples, but to get classifications, to be able to say, well, not only are we building examples, but these are the only possibilities, and to be able to sort of give a complete classification of this kind of singularity formation. This is sort of the very general picture. So there's been, of course, an amount of works done on this kind of problems. In particular, in the case of the heat equation, where the maximal principle is available and much more information can be taken on the initial data. In the case, of course, in the case of semi-linear problems, but also in the case of quasi-linear problems, and all these works I'm mentioning here, I'm just mentioning a very few, all deal with this question of how do I start from a smooth, well-localized wave packet, and how do I get the evolution to lead to the concentration of my non-linear wave. Let me say that for the problem that I will mention, and for the specific kind of work I will mention today, there is this series of work by Martel and Merle at the end of the 90s, which clearly put into the field a new set of intuition and of approach and of techniques which have led to tremendous development. So there is really a change of nature, from my point of view, on the analysis since this very pioneering work by Martel. Of course, if you mention the singularity formation problem, there is a very famous one, which is the question of singularity formation for the incompressible fluid equations. I have nothing to say about this problem, except that it's probably a very beautiful and difficult one. But conceptually, it exactly fits into the same kind of thing. It's a problem where you have very nice initial data, and you ask yourself, is it possible that some singularity occurs? And what we're going to do today is answer this question, but on certainly simpler model than this one. All right, so let me go back to my nonlinear Schrödinger equation and just tell you a few words about structure. Okay, because this is not any equation. This equation has a very specific structure. So U is a complex valued function. Okay, and then there are two quantities. This is induced by the Hamiltonian structure that I conserve by the flow. I have energy, or Hamiltonian, which is this quantity here. So this is the kinetic energy, this is the potential energy. And I have a minus sign here, which reflects the fact that I have a focusing problem. And the total probability density of my wave is preserved. The integral of U squared integrated over space is conserved along the evolution. So you see, if anything like singularity formation is happening, it has to happen, but to be consistent with these two conservation laws, which you should think are the two constraints which I have from scratch on the problem. These are the only two, these are two information that I have for free, and essentially you should think that these are the only two informations that you have for free. Anything else you have to work for. And there is a very important number, which is this number here. So I should say that X is in RD, P is the level, is the power nonlinearity, or the total here is U to the P. And then there is this very important number, SC, which is D over 2 minus 2 over P minus 1, which is the so-called critical Sobolev exponent, and which is a way to classify this equation. So let me just tell you very briefly how you compute this number. It's very simple. There is a dilation group that's acting on the set of solutions. That is, if U of T and X is the solution to my equation, then I can form another one. So give me a parameter lambda. And if I dilate space by lambda, I have to dilate time by lambda squared. And then to fit with the nonlinearity, I have to multiply this function by this factor here, which is dictated by the nonlinearity. So it's an explicit way to make waves more narrow or more spread, if you want, just by playing on this parameter lambda. And then the question I'm asking, and a priori there's no reason why it should be a relevant question, but I'll tell you what it is how many derivatives measure in L2, that is in which Sobolev space does not see that I am changing the size of my solution. Right? So it's a very simple computation. You'll see that if you ask for this identity to hold, it will hold only for this critical number, which is D over 2 minus 2 over P minus 1. Okay? This is the so-called critical Sobolev space. And as it turns out, the critical space is, if you want, this is the minimum regularity that you need to control your flow. If you want to be able to really dynamically say interesting thing about your flow, you essentially have to be able to say something at least about this critical norm. So from there, there are 3 levels of regularity on the board. There is the level of regularity of energy. This is one derivative in L2. This is one conservation law. This is the level of regularity of this second conservation law, which is mass. So this is 0. And the third level of regularity is the one which is given by the scaling symmetry. It's the critical space. Okay, so now from there are several kind of problems. You can sort of classify, if you want, in a very rough, I mean, this is a very rough manner, but this is already a way to understand what's going on. And there are, in some sense, 3, at least, in fact, 4 kind of problems. So there are 2 critical problems. There are 2 special problems. Why are they special? So it's the case when SC is 0 and when SC equals 1. Why are these problems special? Because these are problems where the scaling of the equation meets a conservation law. Okay? So SC equals 0. So so when P rises, SC is going up. Okay? SC is an increasing function of P. So when you raise the nonlinearity, when you reach SC equals 0, it corresponds to the smallest nonlinearity for which blow up is possible. That is, this is the first nonlinearity for which you can have something like singularity formation. I will come back to it. And because the L2 norm is conserved, if you form a singularity, the L2 norm cannot blow up because it's conserved by the flow, but as we will see, it will concentrate. Right? This is typically the concentration phenomenon, which is the heart of the matter. So this is the mass critical case. The other critical problem is the energy critical case. So this is what happens when I raise the linearity. So I raise the value of P, and I reach this energy critical case, which is completely borderline in the sense that the Sobolev norm that I control, which is essentially H1, if you want, is just borderline for my Cauchy theory and to propagate my flow. So in some sense, it's a completely borderline case. And if I go above, if I take a nonlinearity, a P, which is even stronger, then I reach the energy supercritical case. And very roughly speaking, you should think that when you are in an energy supercritical setting, what happens to you is that the Sobolev norms, the regularity that you need to control to actually control your solution, you're asking for more than what is given for free by conservation laws. This is the typical energy supercritical structure. What you know from free is too weak to actually be able to say something clever on your solution. It means that you have to dig dynamically for more information. Okay, so I'll report today essentially on these 3 cases and explain you what we've understood on these 3 kind of problems. All right. So let me tell you about the mass critical problem. Okay, so SC is 0. So the typical example is the cubic 2D. So this is what the numerology is about. So and again, it's the first nonlinearity for which blow up is possible. So this is one of the reasons why this problem was sort of more focused on, because it's really the first problem where singularity formation can happen. So the first thing you want to know about this problem is that indeed, as I promised, there are solitary waves. That is, there are solutions that are propagated without the formation, and in this case, they correspond to time periodic solution. So if you plug this ansatz into my equation, you will need to solve this nonlinear elliptic PDE, and this can be done either by ODE methods or by variational methods deeply related to the question of sharp Sobolev type inequalities. And in fact, the variational structure of the problem and the conservation law imply this remarkable thing that was observed by Weinstein back in 1983, which is that if you take an initial data, which is small, and smallness means in the sense that the critical norm is less than the critical norm of the ground state. Remember that the critical space is L2. So if you are small enough in a critical norm sense, then actually all your solutions will be global in time. There will be no singularity formation. And it's even better than that. You can show scattering, meaning you can show asymptotic linear behavior. Okay, so what does this mean? It simply means that not only do you have a solitary wave, the solitary wave is the first nonlinear object, right? Anything below it will have an asymptotic linear behavior. It's the first solution that has a nonlinear behavior. So from there, a very natural question is, okay, so if I'm below my ground state, essentially I'm attracted by 0. So if you think in terms of ODE, you have this special solution Q. It's obviously unstable, because if I just go below it, I end up with something that goes to 0. The natural question is, can you describe the flow near this solution? Right? If I give you a perturbation of this ground state Q, of this initial solution, can you tell me what the solution mu of T on X is going to look like? Which is sort of, it's the less ambitious thing you can ask for if you want to understand all solutions. Let's start with understanding just the solution close to this ground state. Right? This is the simplest problem you can think of. And what do you expect? Well, what you expect is that the scaling instability of the ground state solitary wave can be excited. That is, what's going on here is that, again, you have a scaling group that's acting on the set of solutions. So for each fixed lambda, if you want Q e to the IT, the solution, so I can make a solitary wave which is either very narrow or very wide. And what you expect is that dynamically you can form solutions such that they will want, the scaling parameter will want to drift along this family of solitary waves. That is, solutions which initially have a lambda, say, of size 1, they are not concentrated, but dynamically the flow is such that it forces the solution to concentrate and this lambda window to become smaller and smaller. Okay, so what you want to do is you want to split your solution, if you want, into a particle-like motion plus a wave-like motion, and you want to understand the trajectory, lambda, x, gamma, which are induced by the symmetries of the problem, and what does singularity formation means. Singularity formations mean show me that for at least certain solutions, lambda is going to go to 0. Okay, and once this is said, you enter a very classical problem which has attracted considerable attention in very different fields, which is how do I extract from the infinite dimensional PDE, which is driving U of T, how do I extract the ODE, the finite dimensional ODEs, which drives my parameter lambda, x of gamma, and how do these guys couple? And more importantly, do they couple? Is there a universal coupling? Is there a universal way to produce such kind of bubble, or on the contrary, can I do anything I want? Right? This is exactly the kind of questions that we want to ask. So one of the first result in the direction of understanding the flow means the ground state was the proof of the so-called log-log-log, which was achieved through this series of work. First, this work by Galidin, Perelman in dimension 1, and then this series of work by Mer and myself on dimension less than 5, in particular in dimension 2. And what we prove is the following. We prove that indeed you can excite the scaling instability. That is, what you can do is that you can construct an open set of data arbitrarily close to the ground state. Okay, so open means that the kind of singularity I'm describing is stable, such that indeed, to leading order, the solution will form, will concentrate the bubbles. That is, this lambda of T is going to go to 0. So I'm clearly forming a singularity by concentrating the L2 mass. But the speed at which this will occur is not anything. It's completely rigid, and it's given by this very funny double log correction to the so-called self-signal speed, right? So you have this very funny law, which is the so-called log-log-log. So this log-log-log was conjectured in a series of work by Landman, Nicolaou, Sulem back in '85. And let me say that, in fact, there were several conjectures on what the stable growth speed for the mass-critical MLS should be. And really, what's been done here is absolutely spectacular back in '85. And you have both a very clever heuristic argument and very sharp numerics to actually be able to predict this kind of flow. So this is the first, this is exactly in the spirit of what I was saying. This is the first, if you want, this is the construction at this point. This is about constructing spatial solution, and here it's more than just one construction. The construction also displays an open set. So not only does this regime exist, but it is stable. Okay? You have stability of this kind of thing. So something, you know, we've known, so you can now be more ambitious, okay? So this is just one construction, so now can you hope to classify? Can you say that these are the only possibilities? So an NLS, it's something you know from scratch. There are other blow-up regimes, they all live close to the ground state, and there are many other possibilities. So actually the classification problem so far near the ground state for NLS is open. But we could do this, and we started in this series of work by Martel and Merle, which I mentioned, and we sort of finished this analysis in this series of work, Martel, Merle, and myself in 2012. We could finish this on the generalized KDV equation, which is sort of a deformation. It's a related model to the NLS. It shares some of the structure of it, but it has some very nice feature, which in particular makes the construction of Lyapunov function slightly simpler. And for this model, indeed, we could completely describe, roughly speaking, the instability of the ground state and show that essentially, near the ground state, you can split the world into two open sets, one in which you will dive again into linear regime, one in which you will have the same kind of singularity formation, and you can completely compute the solution in this case. And as you should expect, when two open sets live close to each other, on the threshold, there is indeed a manifold, and the manifold is called dimension 1, and the behavior of the manifold is the solitary wave behavior. Okay, so if you want the body space vision, you can indeed do it on the generalized KDD equation. And what's important here that this is indeed a complete description of the instability of the ground state. So once this is said, this question of completely describing the flow in the ground state, let me mention this beautiful program led by Nakanishi and Schlag, who typically prove with different approach this kind of result of existence of a manifold, stable manifold close to the solitary waves with blob side and scattering side, mostly in the supercritical zone. But conceptually, these are exactly the same kind of questions. All right, so this is essentially what we know how to do on the mass critical case. Sorry, it's the case SC equals 0. Okay, so now let me move on to the energy critical problem, because you see, the case SC equal 1. So there is something here, you know, moving from mass critical to energy critical. A priori, it's not very clear that you're going to enter the same kind of zone and the same kind of problem. In particular, it was essential everywhere in the analysis of the mass critical case that we have a conservation law above scaling, because it's a huge constraint of the solution, and it's something we kept using all the time. So it's very not clear that now I'm sort of completely abandoning the L2 critical, the L2 conservation law. I'm jumping to the energy critical problem. So it's not clear at all that I'm going to face the same kind of a phenomenon. So I could ask this problem on the power non-linearity Schrödinger equation, but let me pose the problem on the Schrödinger map problem, which has also attracted some important attention. So why is the problem energy critical? The problem is energy critical in dimension 2, so where x is in R2. And the criticality comes from the fact that the conserved energy here is just the Dirichlet energy, and that the scaling of the equation is this thing. And as you can check in dimension 2, this is left invariant by the H1 norm here. So I'm typically facing an energy critical problem. So this is the Schrödinger map. The analog would be the wave map problem. So this is the wave analog, and the parabolic analog would be the harmonic. So let me start observing that this problem shares the same structure. In particular, you have solitary waves, which in this setting become harmonic maps. So these are stationary solutions to your equation. So these are simply solutions which satisfy U wedge Laplace equals 0, but which these constraints that you have to be a vector on the S2 sphere. Okay, and actually, if you want to understand harmonic maps, and if you want to understand the variational characterization of harmonic maps, you have to remember that a map from R2 into S2 has a degree, which counts the number of tours. Right? If I make one tour on R2, I have to count the number of tours I'm making on the sphere, and this is the so-called homotopy degree of the map. And now in a given homotopy class, that is, if you fix the integer k, then you can minimize the energy in this given homotopy class, and you will find that the minimizers are given by a well-defined unit function, which I call qk, which is the exact analog. This is my ground state, okay? But it depends on this number k, and actually, to have non-trivial minimizer, I need k to be greater or equal than 1. Okay, and then the problem takes the exact same form. The question is, okay, so can I, again, understand the flow via qk, and in particular, can I excite the scaling instability associated to my equation? Because again, I have this scaling invariance here, and is the scaling instability a mechanism for concentration of the wave? So, blob for the Schrödinger map is a tricky problem, because it's one of these problems that there is no simple reason to believe that such a singularity formation will occur. In particular, there is no simple algebra like you may have on the power nonlinearity analysis to ensure that for specific solution you cannot be global. So this kind of obstruction was not known, and numerically it was not clear at all whether indeed this kind of singularity formation could happen. For the wave map problems, which is the wave analog of this problem, there's been a lot of activity from 2000 to 2010 of these kind of questions, in particular in two directions. The first direction was to show that, indeed, if something like singularity formation occurs, then you have to bubble out a non-trivial harmonic map. And in particular, if the geometry of your target, so in this case it's the S2 sphere, but it could be something else, if the geometry of the target is such that you don't have a non-trivial harmonic map, then this is the way to prove global existence, right? And there's been tons of development on this question. And in the case of S2, of course, we do have non-trivial harmonic map. I just showed them to you. And the question of singularity formation remained open for a while and was solved in these two pioneering works here by Krieger-Schlatt-Tataru and Rogniansky-Sterbens, who indeed were the first one in a slightly different setting to be able to show that indeed you can excite the singularity formation, and they were the first ones in the case of the wave equation, of the wave map equation, to describe this kind of singularity formation. Okay, but for the Schrödinger map, the question actually was a little bit more tricky in the following sense. First, you have this beautiful series of work by Gustafsson, Karen Tsai, and Gustafsson, Nakanishi Tsai, who show you that, so you have this number, the homotopy degree, and they tell you that if you look at the associated ground state, so for this large enough homotopy degree, then actually you will not be able to excite the scaling instability. It's just not true. And in fact, what you can show is that the ground state is stable. It's a bit asymptotically stable. That is, if you start close to this guy, you will asymptotically in time, will be global in time and converge to this to this solution, and you will not see anything like singularity formation. Okay, so it's not because you have an energy critical problem with an non-trivial ground state that you will form a singularity. Certainly not. You have a counterexample. For k equal 1, which corresponds to, if you want, when you compute the energy of qk, k equal 1 is the fundamental. It's the smallest one, so it's in some sense it's the smallest energy. For k equal 1, you have another result against singularity formation, which is a beautiful result by Begenaro and Tataru, who show that they could construct an open set of data near the ground state again, so they could put a ball around the ground state, but not in the energy topology, the stronger topology. Actually, it was an L2 also topology. And for these perturbations, they could show again that there's not going to be any singularity formation. They could start seeing some instability, exactly like Martel and Merle showed back in '98 for the generalized KDV equations. You could see that indeed something funny may happen, but this is still a global existence result. So this problem was solved. So I'm writing down here a series of papers from which a methodology emerges for the construction of blow-up solutions for all these problems. So it really started in this work with Igor Brodensky and the wave map problem. Then the blow-up for the k equal 1 Schrödinger map was proved in this work by myself, Merle, and Rogniansky. And then we further studied the parabolic version of this problem in this series of work with my student Remy Schreier. And what the outcome is the following. If you want, the generic theorem is the following, is that indeed we can excite the scaling instability. It is indeed there, but you have to excite it in a stronger way if you want than what Begenaro and Tataru did. And what you can do indeed, you can find sets of smooth, compactly supported initial data, right? Absolutely a regular one, such that indeed you will concentrate your energy. That is, indeed, you will drift along your family of solitary wave with a law given with a certain scaling parameter lambda of t, if you want, which is computing the speed of concentration. And the speed of concentration is typically, for the kind of data that we consider, the speed of concentration is typically something that is completely rigid and which is given by the two leading order by these sequences. So it's t minus t to the k modified by some logarithmic correction where k is an integer greater or equal 1. And essentially the idea behind this is that if you have a fundamental, which is k equal 1, and you have excited modes with higher and higher direction of instability. So depending on the problem, this can be stable or not, but we can compute actually, at least locally, the instabilities associated to this bubble. Let me say that in this case of the harmonic heat flow, this blow-up speed were conjectured. There is a very beautiful formal paper by Berg, Ussoff, and King, who were the first one to come up with this algebra here. This is the so-called match asymptotic technique, so there's sort of cooking recipes to understand this kind of law, and somehow we indeed find that these people are absolutely correct. Okay, so what's behind this result? What's behind this result is the following thing. You see, for example, so when k is greater than 3, there is no singularity formation. But when k equals 1, there is singularity formation, and there are these very funny laws that come up. So how do we compute that? Well, what's going on here is the following thing. What you discover, if you like, is that if you give me my ground state, if you give me my soliton, what I need to do, I need to understand my soliton very well. And in particular, I need to understand, you should think of your soliton, it's a nice bubble, okay? It's nice, so maybe here it doesn't go to, of course it's a little bit misleading, but it doesn't go to 0 at infinity, but let's say the gradient to leading order is going to go to 0. And what I need to know exactly, I need to know how this thing behaves at infinity. And it turns out that the asymptotic behavior of the ground state at infinity is intimately linked to the question of singularity formation, and in fact it's linked to the question of how I'm going to evacuate my energy. That is, my wave wants to concentrate, the rest of the energy wants to be evacuated, and this whole mechanism is the way to derive the ODE for the scanning parameter lambda of t. So you should think that you give me the soliton, we have a way to compute the ODE for lambda, and then the question is, does the ODE allow for solution such that at time 0, lambda of 0 is 1, and infinite time, lambda is 0? Okay? So if you do that for k greater than 3, you will discover that no, the ODE is such that there is no way you can link lambda, you can make a path from 1 to 0. Okay? But when k equals 1, the behavior of the ground state, of course, depends on k, and indeed, you discover that you can do it, and you can do it with these funny laws. Okay? So if you want, the first step of all this is precisely to understand this, to have a simple way to link the exact structure of the ground state, so that's my elliptic object. Right? How do I link my elliptic object, the sharp structure of my soliton, to the dynamical understanding of the law for the scanning parameter? Okay? This is extracting the ODE from the infinite dimensional PDE, if you want, near my special solutions. Okay? And once I have done this, of course, I need to close my flow. I need to control the error. I need to indeed show that these formal constructions make total sense. And here we developed to do that a robust energy method, which really is about directly controlling Sobolev norms of the solutions. Let me just say a word about this quantized law. I mean, you see, we see this quantized law, but in fact, what emerges from this Ponian work, Regenschlag-Tataru, and also this further series of works, is that, in fact, you see this quantized growth rate, and you should think that, well, maybe it is such that we are extracting a universal finite dimensional dynamic from the infinite dimensional PDE. But in fact, it's more complicated than that. It is still an infinite dimensional PDE. That is, you can now think of this solution, make them interact with other parts of the waves, and create whatever growth speed you want. Right? But this will correspond, if you want, to different zones of phase space. Everything is about the topology in which you allow for the perturbation near the ground state. Everything is about the norms. It depends on where you are and in which region you are. All right. So what's the outcome of this? What's the outcome of it? The outcome is very clear. Is that you give me one of these equations, you give me my solitary wave, and then you tell me how this solitary wave behaves at infinity, and then we can start computing. Okay? Independently of any subcritical, critical structure, we can start computing formally whether or not such a singularity formation will occur. So this is something we recently did in the energy supercritical setting. So now let's go up. Let's make even more complicated, greater values of P. Let's go very much up, and then it's very simple to see. I mean, it's been known for a while that you do have stationary solutions again. I'm sorry. So now I'm going to the power non-linearity NLS again. I'm abandoning the Schrödinger map, even though I could do it there as well. But, so for P large nothing, even in the supercritical setting, it's very easy to see that you have again solitary wave type solution, which in this case would correspond to stationary solution. Right? There is a change of nature in the solitary waves. When we are below energy, these are time periodic solutions. Above energy, they are stationary solutions. And the thing is, this solution, you can essentially, you know everything in the radial setting, you know everything you want on it. You can compute absolutely everything you want, and in particular, you can compute its shape at infinity. So because of that, you can start computing whether or not, you can start computing formally the dynamical system for lambda. And what you discover is that there is a change of nature in the problem, and in particular, when the critical space becomes large enough, above some universal number here, S star, which depends on dimension only, then which means that if P is large enough, actually the structure, there is a change of nature, there is a bifurcation, if you want, there is a change of nature in the asymptotics of the solitary waves. Right? So you give me my equation, it produces a soliton, but the nature and the behavior of the solitons absolutely depends on P, and something is changing when SC is large enough. So my claim is that then what we did is that we run, if you want, the formal construction, and what we could do recently is indeed show that this mechanism of instability, this mechanism of scaling instability of the solid wave, of the solitary wave, can be recovered for the exact same reason, provided indeed that SC is greater than this S star. And again, this has nothing to do, if you want, this condition here really has to do with the structure of my soliton in the energy critical setting. Okay, so what do we find here? We build solution, which again concentrate a solitary wave, and they do it again in a quantized way. So there are no logs anymore, but this is just what the system of ODE gives, and you have against this quantization phenomenon of the lambda of t type of solutions. So there are two things I want to say about this. The first thing I want to say is that the first time that such kind of solution in the energy supercritical setting was seen is in this work by Eero Velasquez back in 1992, and it was made completely rigorous. And this is a work by Martin Lemaire and Mizuguchi, but it was really for the heat case in the radial setting, and there the use of maximal principle is absolutely everywhere. And actually, I think it's fair to say that the point of view, in particular in these two works, on the problem was very different. What we're doing here really is we are building a bridge between the two critical problems, which were SC equals 0, SC equals 1, and the supercritical enough problem, which is SC bigger than this number S star. And what we're showing, in fact, what's behind this analysis here, in that, in fact, there is nothing special with critical problems. In fact, all these ideas can be propagated to energy supercritical settings as well. Okay, but of course, there is a price to pay when you are in the energy critical settings. What you have to do, again, when you are energy supercritical, your problem is that your conservation laws are extremely weak. So you need to find a way to actually control your sub-LF norm all the way to criticality. And then there is something essential here. What we're doing is that we are building some Lyapunov functionals, which are Lyapunov functionals only in the kind of regime that we are looking at. Right? This is all about controlling your flow, but this can be done only because indeed we are forming a very special kind of singularity. And let me also say that an important thing is that all these solutions emerge from smooth, compactly supported initial data. Right? These are very nice data, which indeed are going to concentrate in this way, and of course everything is in the Trudeau here, and the description of the Trudeau. So let me conclude, just very roughly on what's been understood. Well, I think what's been understood, and it's really the combination of all these works with different teams. What's fairly well understood now is the dynamical understanding of one concentration phenomenon, that is this bubble concentration, and with solitary wave profiles, and it occurs in three cases. It occurs for the two critical cases, and also when we are energy supercritical. But this numerology is not dictated, if you want, only by the structure of the equation. It's dictated by the structure of the ground state. It's dictated by the structure of the elliptic problem, which is the key toward this algebra. You change the problem, you change this algebra. And what's behind this dynamical understanding is the derivation of a new Lyapunov function. I mean, all these problems are about having, of course, heuristics for the construction, and then it's all about closing your estimates. And we know when you do dispersive waves, nonlinear dispersive waves, it's all about estimates, it's all about decay, it's all about getting rates and good enough estimates to actually close your estimate. And here, Lyapunov function will play an essential role, and I claim that what we're doing is a robust energy method. And in very few cases, we can do more than construction, we can actually classify, but this is still, like we did on the KDD equation, but this is still fragile analysis. This is, again, very fancy Lyapunov functionals, and it's not so easy to propagate it to other problems. So let me mention a very few open problems. One very excited open problems is the question of continuation of after blow time. Solutions blow up, but then what happened next? Can we make sense of the flow after the singularity formation, and is there a natural way to continue the solution after that? This is something you cannot address if you first do not know well the singularity formation. Okay, so now we have a bunch of examples, so we can hope to be able to answer this kind of question, at least on these examples. Another very funny question is the question of the geometry of the blow-up set. I've shown you solutions that blow up on a point. Essentially, all we know how to do is point in spheres. There are no other examples. I mean, you have to be a little bit more precise. But really, the question of what kind of geometry is possible is completely open. Of course, the question of singularity formation entered the more general question of the question of growth of Sobolev norms in this kind of nonlinear dispersive equation. What we're having here is explicit scenarios. So now you can wonder whether these explicit scenarios can make sense in other settings. And this is again another world, but it's just the idea behind is that everything is explicit. You can really start computing. And of course, and this is something very exciting, you can hope. I claim that the method is robust. I claim that indeed, at the end of the day, all we do is an energy method. So if you have a robust energy method, you can hope to extend this to more complicated problems. So this is if you want for the future, maybe one day we can say something about free patterns. So this will be for later. This is the aim for the central issue. So thank you very much.
Thank you. For your nice talk. Is there any questions or comments?
Just
S star. How do you define S star?
Oh yeah. So S star is it's a so-called S star corresponds to a P star.
Yeah.
It's a so-called Joseph Lundgren. It's a Joseph Lundgren exponent. This is exactly this. This is the transition that was perfectly known in the literature. There is a change of nature on the structure of the static wave. This is exactly this number.
Any other questions? If not, let's thank the speaker again.